All right, this is the second in this video that I've been making here, where we're going through a problem set. Let me, advance it to where this one goes. Okay, so the first video just involved earlier problems, but let me just say, like, if you're in my class at New Mexico State, you have a copy of this problem set. If you're not, just when it advances to a new slide, just print the screen and copy that slide. You'll have a blank problem for that page, and you can do it yourself. The idea here is that you watch the video just long enough, or the minimum amount of time you need to do the problem yourself. This is supposed to be a learning tool, and it's like you're doing your problem set in front of me, but I'm giving you hints along the way. That's one way to look at this video. Okay, so we're going to start here with problem 6. Problem 5 was in the previous video, part 1. This is part 2. All right, so this is a standard type of problem. Complete the reaction equation. Okay, this is the most basic type of problem you have in organic chemistry. All right. So what do we have here in part 1? We have a base. We have 2 ketones, or 2 C double bond O compounds. This looks to be some sort of carbonyl group, alpha substitution, condensation type deal. All right, let's look at some other issues here. Alpha hydrogens. Ketone has 1 there, 2 there. This other partner has no alpha hydrogens. All right, it involves 2 carbonyl groups at the ketone or aldehyde functional group stage. Okay, what does this mean? It means that this is an aldol condensation. Okay. All right, so this must be the aldol donor, because this is the one that has alpha hydrogens. All right, what does this mean? Well, it means that we're going to deprotonate this. And we're going to add the anion to the other partner. All right. Okay, so if we look at the immediate process from that, we have 2 sides here. The left side, where we have 1 hydrogen, and the right side, where we have 2 hydrogens. Recognize that this is being done at reflux. So this means there's also a dehydration step. And this can only happen if the donor has 2 alpha hydrogens on the same carbon. All right, so we're going to deprotonate one of these hydrogens right here to get this started. All right, so what do we do here? We're going to pull that off. That's a resonance structure. It's the enolate. And I'm going to use this resonance structure to show the mechanism here, because this resonance structure sort of tells us the anion reacting with the electrophile. The enolate is probably the more realistic, but the reaction diagram is going to be messier because there's more arrows. So I'm going to just draw the simplest, most clear-cut picture I can using the alpha carbanion resonance structure. All right, that's going to then add to this one. All right. Okay, so there we go. That adds. Crap, why do I get a call when I'm making a video? That sucks. Okay, sorry about that. All right, so that's the initial product of that. We're going to protonate with ethanol. And because this is being done at 80 degrees, this means we're going to lose water. Okay, we're eventually going to make this compound here. Let's just go through the mechanism of the dehydration process in this one incident right here. Okay, so the ethanol and the ketone have a very similar pKa. So when a strong base sees the alcohol, it can remove the proton from the OH group. It can remove the alpha hydrogen on the right side. It can remove the alpha hydrogen on the left side. It can make hemiacetal, and all those things are happening. But the only thing that moves us in a forward direction to the thermodynamically most stable product is removing this proton right here. Okay, so removal of that going to make the anion there. Again, enolate would be a better resonance form, but I'm just trying to get us to the final result as quickly as possible. And that produces that, and this is going to produce the eventual product. I know that I'm giving you more information than this problem is actually asking for. It's just in these early stages I'm going to go through the mechanism. That's the product right there. Okay. All right. What other questions might people have? Okay. I've been told that OH minus is not a good leaving group. How come it's a good leaving group here? Good question. Okay, all right, that's because it's already got a negative charge, so it's already fairly high energy species. So it can kick out the OH minus because it's already an anion. If we look at, this had a pKa of about 20. Water has a pKa of about 16. Therefore, in an acid-base sense, it's actually favorable to kick out OH minus. Okay, you're actually producing the less basic compound. OH minus is less basic than the enolate anion. All right, let's look at the second question here. Epimerization. Why is that reaction going to the right? Okay, these have the same formula. Therefore, this must be an equilibrium reaction. That must mean this compound is more stable for some reason or another. It's cis, but oftentimes cis is not as stable as trans, but it seems like cis is more stable in this case. All right, so what do you do when you see a cyclohexane ring and you want to determine which of the cyclohexane rings is most stable? I'm thinking here of a type of furniture, a chair. Okay, so we would want to draw a chair. All right, so let's draw a chair. Okay, let's put a methyl up for here. I'm going to put this as my that carbon right there. Methyl up and equatorial. I'm going to skip over a couple of carbons. That means I need the methyl down at this carbon. Down is clearly in the axial direction. There's hydrogen there. There's the carbonyl. All right, so that's these are the species we have here. Okay, let's do a ring flip. Okay. All right, so there's methyl up, methyl down. Both of these are pretty much equal in energy, but the net result here is that one methyl is equatorial, one methyl is axial. And if you do the ring flip, you actually end up with the same situation. Just a different methyl is axial versus equatorial. All right, let's look at the compound on the right. Okay, so the product compound looks like this. Okay, this is in equilibrium with its ring flip. Sorry, can't see that all that clearly because of that. But this is going to be very minor. So we're not going to worry about that, okay? Of all the four compounds I've depicted, this is the one where the methyls can be equatorial in the most stable conformation. So therefore, when we pull the proton off here, this is we're going to remove this hydrogen here. Make the enolate. This time I'm going to draw the enolate because this is very important here. The enolate is flat, okay? sp2. One side is the same as the other. Therefore, we've lost the original stereochemistry when we make the enolate. And the only thing that's making this reaction go to the left or right is equilibrium. This is a system at equilibrium. When the system's at equilibrium, delta G equals minus RT ln KEQ, which just means that the more stable compound is favored at equilibrium. The more stable compound is the compound on the right. Okay, let's do these. All right, what's happening here? This is an alpha-beta unsaturated ketone. And again, we're starting with a blank page. You can do these. If you're not in the class, just print it out and try to do them yourself before restarting the video. All right, so this is an okay, so the issue here is Michael. Sorry, I can't spell addition. Sorry about that. Michael addition, 1,4 addition versus 1,2 addition. 1,2 addition is just addition directly to the carbonyl. Nucleophile minus directly to carbonyl. Nucleophile to the beta carbon. And so there's our alpha and betas there. Okay, remember that alcohols, amines, and thiols do not form stable carbonyl 1,2 addition products, okay? If we did the 1,2 addition product, this would be a hemithioacetal, and this is this would be an unstable compound. It would definitely go back to starting material plus thiophenol. Okay? All right. Okay, so this can only go in a forward direction if it's a Michael addition reaction. All right, so our product here S-phenyl is going to be that. That's our product. Okay, that's the only thing. If this were an exam question, that's the only thing you would have had to provide based on the problem directions, right? It just said to draw the product. That would be the product. Let's just do the mechanism for fun. Okay, so why is the beta position a place where we can add something? All right, so the partial plus is there. S minus adds to give us the enolate. So we still have an O minus species coming out of this. And what's our solvent here? Okay, triethylamine. Okay, so I'll just have that come along like that, and that gives us product. All right, so there we go. There's our product. Okay, what about this one? Next one, we have a ketone and aldehyde in the same compound. What we should suspect here is that we have an intramolecular aldol condensation. All right, so let's draw in all the hydrogens that could be in play here. All right, so these are our alpha hydrogens. All right, the reaction arrows I am giving here now are not mechanism arrows, they're what goes where arrows. Okay, so if I remove one of these protons right here, remove one of these next to the aldehyde, I could make a product where there's a CC bond between that position and the C double bond O position, okay? All right, if I removed one of these protons right here, that means I would be making a CC bond forming a ring between that alpha position and the aldehyde carbon. And if I removed one of the carbons of the methyl group, one of the hydrogens of the methyl group, I would be making a new CC bond forming a ring between that position and there. Okay, if we look at what's the ring size here, it's 4. It's 4 there, and it's 6 here. Okay, the aldol condensation is under thermodynamic control, meaning it is more than likely going to produce the more stable compound. All right, there's no comparison between the stability of a 4-membered ring and a 6-membered ring. The only product we're going to have comes from that combination of aldol donor, aldol acceptor right there, forming the 6-membered ring. Okay, all right, so let's redraw it in a more friendly way. There's 3 CH2 groups. There we go, right there. Again, we're going to be making the bond between that carbon and the carbonyl group carbon of the aldehyde. Okay? All right, so if we look at the aldol product, it's at 80 degrees. We should be making the alpha beta unsaturated ketone. Therefore, that is the product. Let's just look how it would occur in a mechanistic sense. Okay, so as I said before, we're going to remove the proton there. I'm going to draw it as the carbanion resonance form rather than the enoate. The enoate's better, but the carbanion form gets us to the crux of the answer a little bit quicker. All right, so this would be our hypothetical 25-degree aldol product right here. Room temperature aldol product, but at 80 degrees for reasons that we've talked about before. An additional reaction is going to happen that causes the dehydration and formation of the alpha-beta unsaturated compound. All right, so that would be the answer to that problem right there. Okay, this one, what's happening here? We have a base. We have two molecules now of a carbonyl group. Okay, this looks like it's a self-aldol, meaning that when we look at what connects, again, this is not a mechanism arrow, this is a what goes where arrow. We're taking the alpha position there and combining it with the carbonyl group there. At 25 degrees, that means there's not going to be a dehydration. Meaning that we're going to get the beta hydroxy carbonyl compound. And not the alpha beta unsaturated. Not the alpha beta unsaturated carbonyl compound. All right, so what happens here? We're going to remove one of those protons. And we don't really worry which one because they're all equal since the two molecules are the same. That's what makes this self-aldol a very selective process. And then we're going to protonate that. And that's our product. Okay, let's look at some things that we should realize about the self-aldol. All right, 1, 2, 3, 4, 5. There's 5 carbons. That means there needs to be 10 carbons in the product. And what do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good, okay? All right, if we do the alpha beta thing, alpha beta, we should have a hydroxy group on the beta position and no hydroxy group on the alpha position. Okay, all right, so we should make a beta hydroxy carbonyl compound because the reaction is being conducted at 25 degrees C. All right, this is to provide the reagent. What happened here? Alpha beta unsaturated ketone looks like we added an ethyl group to the beta position and we added a hydrogen here. This looks like a Michael addition. Okay. All right, so we want to do a Michael addition to the beta position. Michael addition of R groups is best done by cuprates. Okay, all right, so what would we want to do here? What we would want to do is to treat this with the Gilman reagent It has two ethyl groups in it, diethyl copper lithium. Okay, this is going to give us this, and we're going to do a add weak acid to put a proton on the alpha carbon. Okay, that's not really the important part of this. The important part really is adding the ethyl group to the beta position. Okay, so this is a Gilman reagent. Remember, when a Gilman reagent does not do the 1,2 addition to the carbonyl group, it does Michael addition only. Okay, so we would use a Gilman reagent and not a Grignard reagent when we want to make sure that we're adding exclusively to the beta position in a Michael addition fashion. Okay, I'm just going to finish out this page right here for the part 2 video, and then we'll put the next page in a separate video. Okay, this is a sequential alkylation problem. This sequence of reactions is what we call kind of a package reaction. You see these reactions done in sequence quite frequently. And this is known as the acetoacetic ester synthesis. All right, so let's look at what happens here. Step 1, remove the most acidic proton in the system, which is that one right there. Again, I'm going to draw these intermediates as anions rather than enolates so we can get to the business of this. Anion is then treated here. And in our second step, it's just an SN2 reaction. Okay. So much of organic chemistry can be summarized by first you pull a proton off and then you do an SN2 reaction, okay? And this is a good example of that. Allyl groups are really great for the SN2 reaction, so this is a primary allylic halide, no issues there. Step 3 looks to be an ester hydrolysis. Okay, so we're going to hydrolyze the ester in step 3. And step 4, this being a beta oxocarboxylic acid, undergoes a decarboxylation. Loss of CO2. And that gives us the product here. Okay, recognize that we could have taken cyclohexanone itself and just alkylated it. In practice, that looks good on a piece of paper, but it's a little bit difficult to control the mono versus di versus tetra versus tri versus tetra alkylation. For lack of a better term, the acetoacetic ester synthesis, we say, is idiot-proof. Okay, it's hard to mess it up. Okay, and this longer route often results in higher yields of final product than just directly alkylating the ketone. All right. Okay, what happens here in the second reaction? Ester, 2 of them, base and heat. This looks like a Claisen condensation, which is mechanistically related to the Aldol condensation. All right, so what happens in the Claisen condensation? Okay, we remove the acidic hydrogens. That's the only acidic hydrogen. Okay, the anion that we get, again, I'm going to draw it as the carbanion rather than as the enolate, so we can sort of get to what happens as quickly as possible here. All right, so there's a nucleophile, anion, there's an electrophile. I'm going to do essentially a nucleophilic acyl substitution. Okay. I'm going to kick out the methoxy. The pKa here of a beta keto ester is about 13. Methanol has a pKa of about 16. Okay, so the methoxide that we generated cannot help but come along and pull this proton off. All right, so this is what you actually make until somebody comes along and adds some acid. All right, so somebody will come along and add acid. And you'll end up getting the product right here. All right, one question. So this is the answer. Again, the only thing you had to actually provide here was the answer. The mechanism I've done here is extra. But a common question that people would have on this problem. I had the final product right here. Why did I have to do things after I had the final product? And that's an important point here. And this is because if we look at all the steps here, the deprotonation here is actually very unfavorable. Okay? This is an equilibrium. This is an equilibrium. These are all equilibria. But the most favorable step in the Claisen condensation is the last step of the reaction, the step where you remove that very acidic proton and make the anion. And the anion just sits there waiting for somebody to come along and add some acid. Okay? That's the favorable step. That's the step that makes the Claisen work. If you don't have two alpha hydrogens, okay? You must have two alpha hydrogens. For a successful Claisen condensation. If you don't, the equilibrium actually favors the starting materials, okay, in most cases. So you won't get a successful Claisen condensation unless you can do that final anion formation step. Okay? All right. Let's look at this last one. All right, the last one is going to be mechanistically similar. I'm not going to provide as many mechanistic details as I did for the previous one, but let's look at what we have here. We have two esters. They're different here. One of the esters has alpha hydrogens. This one has alpha hydrogens. This one, no alpha hydrogens. So when we think about who gets deprotonated, it's clear. It's only the one on the left, okay? So that's where we're going to form the anion. Okay? If we follow the reaction that we have above it, okay, same thing is going to happen. It's just that there's now a different ester. Okay, so we're eventually going to make, OET. We're going to add there. kick out. And we're going to make that. We're going to pull the proton off and then put it back in the acidification step. But this is going to be our final product, okay? This would be an acceptable answer for the final product. If you want to get really fancy, you could probably say that final product is a type of ketone that might be more stable as an enol, okay? Because it's alpha to one carbonyl and beta to another carbonyl group. So this, I would consider the answer that I circled to be an acceptable answer. But if you looked at the NMR spectrum of the final product, you'd probably find that it looks a lot more like the enol. There's probably in this, there's almost undoubtedly an equilibrium between enol and keto forms. And I imagine that that is what you would see with the final product. Okay, but again, this should be a selective Claisen condensation. It's mixed, but one partner has no alpha hydrogens, one partner does. And it happens that the one that has no alpha hydrogens is probably more reactive. If it wasn't, we could just use it in excess, and we're expecting that this is going to be a very successful mixed Claisen condensation. All right, so I'm going to end the part 2 here. We have a couple of other videos for the other parts of the problem set.